So one big problem of molecular dynamics and Monte Carlo when using periodic boundary conditions are the long-term interactions. Thus, interactions that decay slower than r at the power of minus 3. If we are in 3 dimensions, or if we want to be more general, r at the power of minus the number of dimensions. The problem with this kind of interaction is that you cannot simply make a cutoff without getting a big error. So yeah, of course you can cut them off, but you must remember that even if you try to put some kind of long-term corrections, you won't get some good results. And of course, which are the most important long-term interactions? Coulombic ones. So there are some cutoff methods for coulombic interactions, so charges, dipoles, multipoles, etc. And you already have a problem because on the radius where you make the cutoff, you will have to put a charge on the sphere of the cutoff in order to get charge neutrality. Otherwise, on the surface of the cutoff sphere, you will get some strange behaviors. But again, you would like to find a way in which you have very small, or in theory, it would be wonderful to have no omission of the long-term interaction at all. You want to consider it completely. A method that is used to do it is the Ewald method. And as said, it is for periodic boundary conditions. So let's see a little bit how it's done. The theory behind it is quite easy. What you're doing is divide the coulombic interaction in a long term and in a short term interaction, in a short term and a long term path. The short term will be solved in the direct lattice, and the long term one will be solved in the reciprocal lattice. So it will be in the Fourier space. Instead of making the full sum of all the infinite or huge amount of images that we have from PBC, or simply as we were doing in a naive way, as that would be a conditionally converging series, we are going to split it into strictly converging series. One that will deal the short-term interaction or the short-term part of the interaction, one that will deal with the long-term part. The way we do it is that we will make some calculations in the direct lattice and some calculations in Fourier space, therefore in the reciprocal lattice. What we'll do is, where we have point charges, so for example a positive and a negative one, we will add some cancelling ionic atmospheres, usually Gaussian ones. And this way, in the direct lattice, you will only have short-term interactions. You will do them wide so that we will only have the short-term part of the interaction, of the coulombic interaction. But then, when we are going to do the Fourier transform of all this, we will also re-add some new ionic atmospheres that will perfectly cancel these ones. In this way, actually in the reciprocal lattice, we will only have the point charges because we will have eliminated these ionic atmospheres with their perfect opposite. And then we will do the long-term interactions in reciprocal space, get the results, and remake a Fourier transform of it. Now the question is, why are we using a Fourier transform and are we working in the reciprocal lattice when dealing with the long-range interactions? It's quite easy. At a certain point, we will have to calculate the electric field in a certain point. So the electric field in the point of Ri. So as we have periodic boundary conditions, it will be something like J n Q j R I j plus ml. So we have the periodic box and 4 pi, the constant. But as we are not working on an infinitely periodic system in reality, because a computer cannot go to infinity, we will have something like a normal sum of j to all the particles q j r I j, and of course the constant that I always forget. We will have to calculate this. The problem is that we don't know the value of this. We know how it should look like. As you might notice, I didn't eliminate the self-interaction because we want to have a periodic function, because in this way we are able to represent it as a Fourier series, and therefore, and that's one of the reasons why it's so nice to work on it in a Fourier space. Then we will of course have to put a correction for it. So how are we actually going to calculate this? Now that we know that it's periodic and we more or less know how it should be built. Very, very easy. We are going to use the Poisson equation. This is the Poisson equation, where rho of r is the electric density, the charge density in the position r. This equation is quite complex to calculate in direct space, and that's why we are doing it in Fourier space. In fact, by going around this, so the electric field and the charge density, by using Fourier transforms, we can say that it will look something like okay, so the field with this symbol and the charge density with this symbol means these are the Fourier transforms. In fact, they depend on the vectors in the reciprocal lattice and in the Fourier space. Then we are retransforming with an inverse Fourier transform in order to get this one. So this and this equation are exactly the same thing, because I had the Fourier transform and do the inverse Fourier transform. So that's what we are actually going to solve. And we are able, the interesting thing is that we are able to do this differentiation very, very, very easily. In fact, this differentiation is equal to 1v, the vector of the reciprocal lattice, its modulus, in fact, that's the derivative of this. That's quite easy, because the only part that depends on r is the exponential, and it's very easy to do the derivative of an exponential, while the Fourier transform of my field doesn't depend on the positions in real space. Therefore, we don't have to know its expression to derive it. And now, with this expression, remembering the expression of the charge distribution, of the charge density, we can go on and simplify the equation even more. In fact, we can have something in the form of So this is the new expression of my Poisson equation, but we can split it up in a system of equations. And so by splitting it up and simplifying the volume, simplifying all the parts we are not interested in, we'll get in this expression. We'll get in a system of expressions that are in the form of... So that's the expression we will get in the end. Because if we find... Of course, this expression must be true for each single of my k of my vectors of the reciprocal lattice. So the expression will be so this is actually in the end the expression we have for the electric field in a certain point, of course depending on the vector in the reciprocal lattice. So 4 pi divided the square modulus of the vector multiplied per the charge density. This part, so 4 pi divided k square, is often called green function. So it's often called green function, written shortly with a g. This is actually the Fourier transform of the green function. So I forgot the little hat. So at this point we are able, once we know the charge density, and we know it perfectly because it's periodical, we know our box and we know that it's periodical, so we can express it in a very smart way. We are able to calculate our electric field on a certain point in reciprocal lattice, and then we only need to do the Fourier transform of it, and we will have the long-term interaction in direct space. That is actually what we are interested in. So yeah, it's a little bit of a loop, a little bit of turning around, but in the end it's mathematically much easier than trying to solve the problem in direct lattice. So as said, what are we doing? We have our Poisson equation. We see that it's complex to solve in direct lattice, so we do the Fourier transform and the reverse Fourier transform of everything inside it that could give us problems. And we see that in that case things become much easier, because we arrive to an easy expression as this one. So the very complex second order differential equation, very easy and simple equation. So by solving it in a very easy way, we get our electric field depending on the vectors in reciprocal lattice. And then we will be able to get the full electric field by doing the Fourier transform, and of course considering it for each single vector of the reciprocal lattice. As said, it seems going around, but it makes things much easier, and with the fast methods we have to calculate the Fourier transform, it's a very interesting method, and it's quite fast. And as said, there are methods to make it even faster by changing this charge density. In fact, there are methods, all the methods with the word mesh in it, more or less. So particle mesh, particle mesh Ewald, or smooth particle mesh Ewald, that as the main thing have to change my charge density. Because these other methods do interpolate the charge density on a grid in real space before doing the Fourier transform. They do it in different ways. For example, the smooth particle mesh Ewald uses B-splines. But there are other methods that use Lagrangian interpolation. There is quite a lot of freedom. Of course, once you do this kind of interpolation, the value of our green function will change and the expression of the green function will change. So the green function, the expression for it is method dependent. It's maybe not always easy to find the best green function for your system in order to get the best results, but in the end each method has its own choice. And in this way, by having this charge density being a continuous and smooth and well-behaving function instead of having a lot of point charges gives us the possibility to use the very fast Fourier transform routines that we cannot use if we use point charges. But as I said, all these faster methods, in the end, the idea is always the same: to use the Fourier transform to make the mathematics behind it easier, to solve a very complex equation in a very simple way. If I have an infinite distribution of point charges that are periodical, so exactly what we have with periodic boundary conditions, the coulombic interactions will be in this form. This is the simple standard coulombic potential in reduced units. In fact, there is no the constant 1 on 4 pi epsilon. Now, what is this m? M is a vector that goes from 0, 0, 0 to 1, 0, 0 to all the combinations, then 1, 1, 0, so etc, etc. Then we will get 1, 1, 1, and so on for all the integer numbers. So what are we actually doing? We are considering the interactions inside the true image, the cell we do have. The prime means that we are not considering, of course, the interaction of the cell with itself. Then we will have the interaction of the cell with all its first neighbors, so all the imaginary images of the system, so where we will have to all the values of m 1, 0, 0, 0, 1, 0, 0, 0, 1. Then we will have all the where we have 1, 1, 1. Then of course we will have 2, 1, 1, etc, etc. So we will go on creating what's more or less a kind of sphere of all the cells we do have. So what we're doing is slowly, as we go on with m, is creating more or less a sphere of interacting images, of imaginary images. When we go to infinity, we will have an infinite sphere. On computer simulation of liquids, you will find a much better image of this. So that's what we are doing. But there is a problem. This series is conditionally convergent. Therefore, it converges only if we put all the paths in the right order. But of course, we don't know the right order. So the way to get the series to be strictly convergent is to divide it in two parts. As said before, the long term and the short term. By dividing it in two parts, we will have two strictly converging series. The short term, as said, will be done in the direct lattice, and the long term in the Fourier space. Therefore, we will have to do a Fourier transform of the charges. So once we apply what I said, this is the form of the potential in case if the infinite sphere is surrounded by a vacuum, so by a dielectric, because in this case it will be surrounded by a small dipolar layer. If we want to have it surrounded by a conductor. So if we are interested in having it surrounded by a conductor, we must add this correction. That therefore does simply cancel this last part. So if we have a metal, we simply remove this last part. So now in general, this is the part of the direct lattice. We will usually choose this k, that is a parameter, in order to only have to use m equals 0. And therefore the first box, to have the short-term interactions that are only inside the true image. And then these vectors are the vectors in the reciprocal lattice, are wave vectors, and as you see, these are the planar wave functions that come from the Fourier transform. I hope you enjoyed the video. All the sources and the materials I used to do it are written in the description below. And here is some more content for you. But wait, don't click on it yet. First, remember to leave a feedback in the comments section to let me know what you think about it. Like, subscribe, follow me on social media, links in the description. And if you would like to support the channel, consider to donate on Patreon. Again, link in the description below. See you next time. I'm Maurice Karnbrook for the Computational Chemist.